Yeah, I'll talk about analog filtering functions today. So before talking about analog filtering, like the outline will be what are the basic analog signal processing that we have, and I'll give a basic introduction to filtering, and then we'll go from ideal filters to real filters, like how does the transition happen, and what all are the parameters that are affected when we implement them using real devices, and what are all the parameters that we need to look at when we choose a filter, and those parameters will translate to filter transfer functions, and finally we'll try to realize them using physical components, and we'll also discuss in the process what are all the non-idealities in components that are present. So if you look at analog signal processing in today's chips, these are the primary functions that we'll be doing that are done by any analog design engineer. So attenuation is basically, you must have done any resistor network is an attenuator, and you can also use active devices to fine tune the gain or set a signal at a certain level to not oscillate. So amplification is again a standard function that is used for like power gain or voltage gain or current gain. All those come under amplification, and today we'll be discussing filtering. So filtering is another very important tool at our hand. For example, if we talk about mobile phone, we have a lot of RF spectrum around us. There will be RF filters at the input of antenna to select the signal of interest or the band of interest, and further there will be modulation in the signal chain. It can be either amplitude modulation or frequency modulation, and currently these can be done in digital or analog domain. So in olden days we used to use analog modulation. There are still papers that come out which implement both amplitude and frequency using analog techniques, and then mixing is a standard analog procedure that we do. Mixing is basically converting frequency domains. So if we want to translate, say, a 20 megahertz signal to a 2 gigahertz signal, so that is primarily mixing. And mixing can be we can either up convert or down convert. So again, mixing it's a topic of its own. I think Vic, do you plan to talk about mixing? Okay. From the mixing, okay. So I was just asking Vic, like, do you plan to cover any of these, like modulation techniques? Okay. Okay, awesome.
Sorry, I thought you were like talking to me or something.
No, you're good. So the other, like we have some more functions that we have, like the digital to analog converter, analog to digital converter. So there again, whenever we interface with real world, we'll need the use of ADCs. So when again, if we talk about mobile communications, we are getting signal in RF, which is an analog signal, and we should convert it to, we'll digitize it and then use DSP and other digital tools to demodulate or do any other functions, which will save both energy and also they're more noise immune when we do it in digital. And again, we'll use digital to analog converter again when we are up converting and sending out through antenna, and also when we are talking on phone through the transducers, we'll be using digital to analog converters. Sorry, analog to digital converters. Digital to analog converters. Then automatic gain control is something a very key block. We do not want to saturate a signal chain. So saturating a signal chain meaning if we have the voltage swing from say 0.3 volt to 0.9 volt, we want to stay in between and make sure the entire signal chain is functioning. So the automatic gain control will make sure that no block is saturated and everything is in operation region. And then power amplification is basically whenever we blast a signal into air, we use power amplification because air as a medium is very, it attenuates a lot. So we amplify the power that is coming out. And power supply management is basically the power management integrated circuits. So every chip that you take has PMIC onto it. Either it is integrated onto your processors. For example, if you take any Intel processor or AMD or Apple, all of them have PMIC integrated into it, and they're primarily analog blocks. And signal generation, PLL, FLL, they're all used for clock frequency translations. So whenever you want to say you have a crystal at 10 megahertz, so crystal gives you a very clean clock, and say we want to generate a 2 giga clock, then we'll be using PLLs and FLLs to transfer it based on the phase noise and other requirements that are given by the system level specifications. So just to get a feel for the class, like which functions did you not hear before? Like
I've heard a lot about FLLs.
okay,
Everything else is pretty familiar.
cool. So FLL is not, it's a frequency locked loop.
Yeah.
It's not as premium as phase locked loop. In frequency locked loop, you do not really care about the phase. You just want the frequency to be locked. So the instead of, so in the standard PLL, I'm blanking on the block. So there is the one block that compares the signal will get simplified. You don't need that complicated block. And FLL is much easier to design compared to PLL. Yes, not at the phase noise. So here we do not have, in phase lock loop, you're exactly matching, like you have a constant phase difference that you guarantee. But in frequency lock loop, we don't guarantee. Like if you have like 2 free running clocks, then we can use FLL. So like there is a whole history on how PLL got invented. So they first came up with FLL, and then they realized they're not, the phase is not matching, and then some smart inventor like came up with this phase lock loop, which is the modern day clock generation circuit. I think Vic is an expert in PLL. He's designed a PLL full. So then intro to filtering, again this very basic slide. So filters are primarily to allow any signal of interest and block which we are not interested in. And whenever we talk about filters, we always talk in frequency domain. So when we are talking, for example, about a voice over phone call, so the frequency range of our voice is between, I would say like around 4 kilohertz. So after 4 kilohertz, we will filter out everything, and between 200 and 4 kilohertz is where we concentrate and we do all our filtering. And we primarily use capacitors and inductors to play with the transfer function, because resistor is independent of frequency, but capacitor and inductor impedance depends on the frequency that we choose. So we play, like we'll play with the values of capacitors and inductors to match our filter profile. And like if we talk about like basic applications, if we think about an integrator, so the transfer function of an integrator is 1 by s, right? Like if you think of an integrator and convert it to Laplace transform, it comes as 1 by s. So everybody comfortable with Laplace transform? So when 1 by s, so s is 0, so when we try to plot the Laplace transfer function, so we have a ramp function starting at 0, and sorry, when s equals 0, we have a pole at origin. So whenever we have a pole at origin, it starts falling from infinity, right? Like whenever, like all comfortable poles and zeros. So pole means from that point the transfer function starts dropping, and 0 means the transfer function starts climbing up, right? So when we say 1 by s, so practically the gain at frequency equals 0 is infinity, because 1 by 0 is almost infinite. So the transfer function starts almost at infinity and it starts rolling down from origin. So that's 1 by s in the frequency domain. So that's what here I mentioned, like the amplifier the gain starts rolling off from the origin, and all the if we, after a certain frequency, all the amplitude is almost 0. So that way the circuit will be stabilized against any high frequency input. Like if there is a sudden high frequency jitter or high frequency noise that is coming in, we are immune if we use an integrator which is acting as a low pass filter by filtering out all the high frequency components. And another basic example is if we have a high pass filter at DC, that means we have a 0 at DC, so it is rolling up from origin. So it will block off any DC offsets or any noise that is around DC. So any slow moving noise will be filtered out effectively if you have a high pass filter with corner at origin. A simple, when I mean simple, it is a basic RC. So when you have a resistor and capacitor to ground and you're taking voltage across capacitor, that's a low pass filter. And when you switch capacitor and resistor, that's a high pass filter. So when I say simple single pole, I mean a basic RC. So if we look at an ideal filter, so we have like these 4 main kinds of filter: low pass, high pass, band pass, and band reject. So we ideally want a filter to be something like this. So when we want low pass, we want all the frequencies of interest to be passing and everything else stopping, and the same with high, band pass, and band reject. But in real world, it is not possible due to the implementation challenges and others that we discussed today. So here if we look at it, there are a couple of parameters of interest that we have. So we have the corner frequency of interest, beyond which we want to either stop or reject. And here we have, in band pass and band reject, we have the low pass filter cutoff and high pass filter cutoff. And we call this F0. F0 is generally the geometric mean of FL and FH. So any comments on why this is not possible, like this brick wall kind of filter? So what do you need, like what is this, like if you think about it in equation form, like what does it represent? Right. fall down. That means here we have infinite poles. So each pole corresponds to 20 dB per decade roll off. So this is almost it's, we would say, high, very high compared to 20 dB roll off. So we would need very high number of poles, which is not very efficient. So in real world, we'll have something like this. So instead of this sharp cutoff, we'll have a kind of a transition band, and this transition band is what will lead to different kinds of filters that we have today. So on first is like how, like what should be the slope of this transition band will lead to the order of the filter. And so here we will have still some frequency components that are being attenuated but are still being let into the signal processing chain after the filter. So a band reject filter, if you look at it, you can view this as an addition of low pass filter and high pass filter. This is a low pass and a high pass, and there are standard mathematical functions that we've already come up with for Butterworth, Bessel, elliptic, all of these. So all of these can be represented in these kind of transfer functions. I'll discuss these during my last slide presentations if you have time. So now I'll go through standard parameters that are of interest in a filter. So whenever we want to compare filters, we want to normalize them so that we can compare the transition frequency. So we want to compare like what is the transition band like, and we also want to compare the ripples that will come due to the transfer function that we pick. So basically when we say normalize, we normalize the corner frequency to be 1. So all the, irrespective of the corner frequency, we will get what the amplitude response is and what the slope of the curve is, and if there are any ripples in the stop band or if there are any ripples in the pass band, how are they? Like we will be able to compare the filters, and this will give us a kind of removing all kinds of filter properties, and it will basically give us a nice way to compare the different class of filters. And the second way is the amplitude response. So again, filter is a transfer function. So amplitude response is basically the amplitude as we change the frequency. So for a 2-pole system, the roll off is 40 dB per decades. Each pole gives 20 dB roll off. So this is 40 dB. This is, and each of them will give us a multiple of 20 dB per decade depending on the number of poles we have. And as they mentioned, we generally plot in a log scale so that we get better readings whenever we compare across different input frequencies. And after amplitude, the filter main response is phase response. So in an ideal world, if we consider filter as a black box, we give an input, we want the signal not to be delayed, right? And we want whatever frequencies are of interest should be passed through, everything else should be removed. But because we'll be using real components, RCs, they all have inherent delay in them. And this is definitely a cause for concern, and we should make sure that the phase shift at the output of a filter is always tolerable, if not 0. And every pole, as we know, will introduce a 20 dB per decade roll off. With respect to phase, at the frequency of pole, you will see a phase shift of 45 degree for any input signal. So this is a rule of thumb. So at the pole, you will see a 20 dB per decade roll off if you plot Bode, and if you look at the phase response, it will be exactly 45 degree at the pole, and at 1 decade before the pole, you will have no phase shift, and 1 decade after the pole, you will have a phase shift of 90 degree. So if you have 2 poles, then the phase shift at the pole is 90 degree. So whenever you give a sin omega t and you have a 2 pole system, at the frequency of the pole, it becomes cos omega t as it comes out, because there is a 90 degree phase shift. Is it okay? So for example, if your pole frequency is 10 megahertz, so the filter is very effective till 1 megahertz, because till 1 megahertz there is no phase shift, it is 1 decade below. Between 1 and 10 you will be seeing phase shift. So whenever you are giving an input signal between 1 and 10, we need to be cognizant of the fact that there is some phase shift involved. If we can tolerate that phase shift, we are okay, or not. If we need to choose some other filter configuration, or we need to come up with a scheme where we can compensate for the phase shift. And there is another figure of merit here called group delay. So group delay is basically change of phase with respect to frequency. So again, this will give us a measure on the entire frequency response. Like if you look at this plot, so what this plot tells us is, for example, if we take a constant delay filter, so it has constant delay, and if we take 1, if we take the normalized frequency to be 1 and the delay is around 0.85, so this will tell us what will be the delay of the output signal if an input signal passes through this elliptic constant delay filter. So what's the difference between phase shift and group delay? Right. So here we are trying to relate the phase shift with frequency. So before we are giving, we have an idea of what the phase shift is with frequency. This is tying those both and telling like what the group delay will be like. So this is tying in the frequency information with phase shift and giving us then the group delay will give us that specification. So whenever, okay, let's go to transfer functions. So sorry? Yes. Yes. So phase versus frequency is phase delay. Derivative of phase with respect to frequency is the group delay. So we've discussed, go ahead. Sorry? So the question is, if we have different filters with different group delays? Okay. Right. Correct, correct. That's correct. So we've looked at normalizing the curves to understand how the filter behaves. We have looked at amplitude response, phase response, and group delay. And let's take a quick view at transfer functions. And transfer function is basically given a circuit using Ohm's law, KVL, KCL, finding the output by input in Laplace domain is what will give us the filter transfer function. So if you take an RC filter, a series RC, and you're taking the output between the cap and the ground, the capacitor output and capacitor is tied to ground, then the transfer function will be 1 by 1 plus SRC, right? If R and C are the values of that. So that is a basic transfer function. So as the components become, as there are more components, it will take more time for us to come up with the transfer function. So this is a very generic transfer function. So the order of the numerator is m, the order of the denominator is n, and so whenever we say the degree of the filter, so when we say second order filter, third order filter, first order filter, it's basically n. So if n is 1, then the filter is first order. If n is 2, the filter is second order. And again, this is giving us the roll off of the filter. And this is giving us the zeros. So zeros is again giving us the rate at which the transfer function will go up. So here are the couple of points that we should note. So each pole is minus 20 dB per decade. Minus 20 dB per decade is basically minus 6 dB per octave. Octave is if we double the frequency. And each zero is the opposite. It's just we go in the opposite direction. So all the roots, again, this is all mapped based on a transfer function in Laplace transform. So all the roots can be real or complex. If the roots are complex, they should be conjugate pairs based on the complex algebra rules. And we plot the all the poles and zeros on an S-plane with real axis as x-axis and omega as the imaginary axis. And we always want the roots to be on the left side of the plane, because that means the circuit is always stable. So what does this mean? Like, why does left side of the plane mean it is stable? So it's basically we are making sure that it's always decaying, right? So we never want the denominator to go to 0. We always want the denominator to be as large as possible so that it's always decaying. That's like the intuitive feel for left side. So if you look at this basic RLC response, so now what kind of filter is this filter? So why is it bandpass? Because we have, if you look at the pole 0 plot, we have a 0 at origin. That means from origin, if we look at the frequency domain transfer function, from origin it starts rising up, right? And then we have 2 poles. So it starts rising up, it flattens at a certain point, and then it starts rolling off with minus 40 dB per decade. So whenever we see this kind of transfer function, we can always by default like remind ourselves that this is a bandpass function. So again, like from here to here, this is all standard math, which I will not go into. But like an ideal place would be that whenever you look at a circuit, the ability to come up with a rough transfer function without doing the math is always cool. Like whenever you go to industry and start designing stuff, we'll not have time to sit and work through the math. Generally, they'll either be simulating them. So, and we do not want to simulate without having a gut feel. To get that gut feel, it's always important to have an intuition on what will be the number of poles, what will be the number of zeros, and what are the path for forming those poles and zeros is always important. Yes. Sorry? Sure. So, we have in the numerator we have s by this denominator. So, now given that there is only s in the numerator, so there is a 0 at origin. So, if there is a 0 at origin, then the transfer function will start. We know that wherever there is a 0, there will be plus 20 dB per decade rise. So, it is rising from origin at 20 dB per decade, and then we found these two poles at these locations, right. So, it starts rising at these locations. At one location it will plateau, and the other location will start falling at 20 dB per decade. So, that way we are able to identify that it has a standard band pass filter kind of a functionality. So, this is basically giving us this is S minus. So, this will be the j omega frequency. So, I think this will be a sharp band pass, right. I do not think since we have like both poles located at the same point, I think it will be will have rise and then it will start roll off at 20 dB per decade. So, we will not have a flat band response, we will have some attenuation in the response that we will get. We will never get 0 dB attenuation in this filter. Right.
And that's the number called, I like forget a lot of them.
So, yes, so here we have the omega axis, so it is 3.122. So, that is the frequency at which we have our frequency, the poles at this frequency. Oh, cool. Yeah, it will be cool. Thanks.
So, this side or the back? Which would you prefer?
I can write this side.
Okay. So, the camera can see it from the middle.
Okay. Thanks. So, again coming back to specifications. So, if we look at low pass and high pass, we will be interested in mainly the filter cutoff frequency, and there is this other class of filters called elliptic, and I just put it there, but I will talk about elliptic filters at the end. Corner frequency and ripple frequency, they are very similar depending on the class of filters that we talk about. And there is this other factor called shape factor. So, shape factor is basically like how fast the transition is. We want to know, is it minus 20 dB per decade or minus 40 dB per decade. So, that will give us that spec as well. And in band pass and band reject, the main specifications of interest are the F naught. F naught is the geometric mean of the low and high frequencies, the bandwidth for which we want to filter, and also the other thing is the quality factor. So, quality factor does come in low pass and high pass, but it is of more importance in band pass and band reject, because we have, so like, can anybody tell me like what quality factor is in like your intuitive feel, or what you understand by quality factor?
It's the sharpness. High Q.
So it's the sharpness of filter. What are other definitions?
So this was the skew rate.
The skew rate?
Yeah.
Mm-hmm. So yeah, both the definitions are very close. So whenever, for example, we have a low pass filter, so this is the standard low pass filter that we expect, but this is generally a quality factor of less than √2. But if you have a quality factor, a high quality factor, for example, if you have a quality factor of say 20, this might lead to something like this. So this is due to a high quality factor. So in an ideal situation, we do not want this to happen, because basically we are amplifying the circuit, because this is no amplification and it's just filtering. So this is due to the parasitics involved in the circuit, which are leading to this kind of peaking that's happening. Yes, they also have a quality factor.
But is it dependent? It's not dependent on like FH, FL, right? Those aren't defined.
Right. So like a generic denominator of a transfer function of any second order low pass filter can be written as this denominator of S. So this is the generic denominator for any filter, a second order filter. So this quality factor is what determines the peaking. So if we have a band pass filter without peaking with a quality factor of under √2, we'll have something like this. But as the quality factor increases, we'll have like it peaks and causes, it might cause some instability in the circuit. So this is a shape factor demonstration. So here it is showing like the point at which it reaches minus 80 dB and the point at which it starts 0, like how long does it take for us to reach from 0 dB to minus 80 dB. That will give us the shape factor specification whenever we are designing a filter. So here we have like 4 basic filters, their transfer functions, the pole locations, and how does it look like when we plot a frequency domain magnitude plot. So if we observe, all the denominators are exactly the same. So all of them are a 2-pole system. They have the exact identical poles, but depending on the 0 location, they can either be divided into these 4 main categories. So if there is no 0 at all, then it's a low pass response, right? If we have a 0 at origin, like we discussed, we'll have a band pass response. And if you look at high pass, here we have 2 poles at origin and two zeros at origin and 2 poles in complex domain. This will lead to high pass. And band reject is basically we have the poles on the zeros on the imaginary axis, and the poles locations are again so notch reject. So basically here we are saying we have a pole here, so it starts rolling off, and we have a 0, so it flattens, and again we have a 0, then it starts rising, and then we have a pole, it flattens. Okay, I think I've told this in the beginning. So each pole of a filter will add 45 degree of phase shift at the corner frequency. So this, I will skip this slide because we have covered this. So this is giving us the variation of the phase shift with frequency due to different Qs. So if we take a low Q filter of say Q equals 0.1 and we look at low pass response, so the phase shift is very bad for a low Q filter. So the frequency of 1 is, for example, say our cutoff frequency. The phase shift is already changing by say minus 20 degrees for a very low Q filter, but as the quality of the filter is improving, the phase shift is almost 0 till the cutoff frequency. Any observations here, Vic? Sorry? Yes, 4 kinds of filters. And if we look at the transfer functions, they all belong to one family, right? They are all arctan family, right? Whenever we plot arctan against frequency, we'll have something like this, right? So this is, they are all arctan. So if we look at a first order transfer function, so whenever we want to calculate the phase shift, we'll take this transfer function and then calculate the phase shift. And that will give us tan inverse omega by q for the first order. So as long as you're comfortable with converting Laplace transform and calculating the phase response for a transfer function, this all should be implications of writing the transfer function. I think I'll skip group delay. So there are again, we've been only looking at frequency domain response, right? Whenever we have a black box filter, we have input output. We've only been looking at the frequency of interest. So for example, if we are testing this in the lab, we have a filter that we design. We'll give a sine wave input and we'll check the output in a spectrum analyzer and see what is the change in the amplitude. For example, here we have a signal source. We are giving a sine wave at 1 volt at 1 megahertz, and at the output we got a sine wave of 0.9 volt at 1 megahertz. And then that means there is an attenuation of about 10%. So the filter corner is somewhere less than 1 megahertz, right? And we are not at all looking at what will happen to some random time domain signal, which is of importance whenever we design a filter. So to capture this time domain response, we have two main test sources that we use. We either use an impulse source or a step response. So an impulse response, again these are all purely theoretical. We will not really give impulse response in real world, right? Because impulse response is basically a delta function which has a very high bandwidth signal, right? Like we are have a burst of energy at one frequency and there is no other signal in any other frequency. And the Laplace transform of impulse responses is 1, right? So this is basically whenever we give impulse response, we are primarily checking on the transfer function, and it directly gives us the bandwidth because the input is 1 and we have, say, transfer function f of t. So whenever we input a signal, in time domain we multiply the signal, right? So we have f of t and we give an input of V in. So the output will be f of t times V in. So in our case, since we are giving impulse response, it would be very easy for us to estimate the bandwidth. And then the next response, the time domain response, the step response, which is the second time domain test that we do for any kind of filter. So here there are again two parameters of interest. What is the overshoot and what is the ringing involved. So for example, if we give a standard step response to an input of the filter, there will always be a certain overshoot and there will be a ringing for it to settle. We will never have an ideal kind of filter. So the overshoot and ringing again will give us insight into what kind of filter it is. So the ability to transfer the rise time and the settling time is another key important specification. So in real world, when we are designing in industry, they'll tell us, okay, this is the rise time of the black box I want, and it should settle within 1 microsecond, or it should settle within 10 microseconds, it should rise within 1 microsecond. These are the kind of specifications we'll get as designers, and we should be able to translate these back into filter specifications and start designing. So step response will give us that tool to do that. So I'll skip the devices part. So here I've covered the passive and active devices. So just to give an overview, resistors are expensive and they're very poor. The tolerance is very high in any physical resistor that you put on a PCB, and a resistor that you put in an IC is reliable but is very expensive. It takes up a lot of area, and we should be careful whenever using a resistor. And there are always, all devices come with parasitics, so we should be aware of what kind of parasitics are important and how should we overcome them. And whenever you design, you should have a rough rule of thumb on till what frequency can each component be used, and always look at the resistor data sheet and understand where it should be used. And again, capacitors similarly, they also, again, it stores charge in an electrostatic form, and all, again, capacitors will have non-idealities, and we should also be aware of the magnitude of capacitors that we can use. So in an IC situation, whenever we're designing an integrated circuit on silicon, a couple of picofarads is a pretty high value. In today's technology, they even use 1 femtofarad kind of values, and on board it's very common to see microfarads of capacitance depending on the application. So, and capacitors come in again different packages similar to resistors. Again, here we should be aware of the parasitics involved in a capacitor. Every data sheet will give you the parasitics involved in that device, and whenever we simulate, we should make sure we take that into consideration. Inductors are the opposite of capacitors in certain way. So, here we are storing energy in electromagnetic form, and capacitors, inductors, they all have like the quality factor, and again the quality factor is determined by the parasitics involved in the inductor and capacitor. So, if we look at the quality factor definition, if the parasitic resistance in the inductor is 0, then we have infinite quality factor, we have an ideal inductor. But typically the parasitic resistance is around 3 or 5 ohm, so that will reduce the quality factor drastically in an integrated circuit environment. I am like 5 minutes out, so here what do you want me to do? Okay, then, so what I have in the plan is like I have like filter realizations, and I talk about passive LC, then I talk about integrator, then I talk about this general impedance converter. So, have you come across this topology before? So, generally, so this kind of inductors are difficult to fabricate. So, we use active devices to realize an inductor. So, this gives us the ability to come up with any inductor that we want. So, if we replace those impedances with resistors and this capacitance, so we will get, this will be the transfer function between these two terminals. So, it is C R1 R3 R5 by R2. So, as soon as capacitance comes into numerator, so so there is some random value and there is S. So, whenever S some constant is an inductor, right. So, inductor is nothing but, like whenever we talk about inductor, we call it SL, right. S is j omega. So, whenever S is in the numerator and there is a constant value, we will call it an inductor. So, this is an inductor in certain frequency range, and this is again realizing negative resistance. So, we will realize negative resistance because we have two capacitances. So, if we go back to this, so here Z is Z1, Z3, Z5 by Z2, Z4. So, this is the effective impedance between the two terminals. So, if Z1 and Z3 are capacitances, then we will have Z1 is 1 by SC1 and Z3 is 1 by SC2. So, Z1, Z3 will give us 1 by S squared C1, C2. So, whenever we have S squared, we have J squared omega squared. So, J squared is minus 1. So, that way we can realize negative resistance in certain frequencies. So, all of these techniques will come in hand whenever we want to be smart about coming up with components to realize transfer functions. So, I will give this to Vic to transfer, and I was talking about Butterworth Chebyshevelliptic all the while. So, I will just finish it with Butterworth Chebyshev and elliptic. So, Butterworth, so whenever we talk of a filter, we talk of a numerator and denominator. So whenever we pick the poles on a circle, on the unit circle, that we call it a Butterworth filter. So the advantage of having a Butterworth filter is, since they're always on this unit circle, we'll always have a flat response. This might be rushing, so then the Chebyshev is, instead of a circle, we'll take an ellipse and take the poles. Then what will happen is, here in Chebyshev case we always have, in Butterworth case we always have the magnitude to be same. But in this case the magnitude need not be same. So this will cause some ripples, and the ripple can be either restricted to stop band or pass band. Depending on pass band or stop band, we'll call it type 1 or type 2. And elliptic is a superset of Chebyshev and Butterworth. So in Chebyshev and Butterworth, there are only poles, there are never zeros. But elliptic will also start introducing zeros, and due to zeros, we'll have ripples in both the stop band and in pass band and stop band. So these are the three main filter categories that you'll come across, like the basic categories that you'll come across. As you progress, there'll be other categories like Bessel functions. So any mathematical function that you can think of can be implemented in a circuit. So as the circuits have been invented in 40s and 50s, as soon as we got a resistor and capacitor, maybe before. So people have come up with smart functions to isolate signals or filter signals. There are a lot of math functions. You can always think of ways to implement them. Sorry, I should have planned it better. So please reach out to me if you want to discuss analog circuits or want some free advice on